as our speaker. Lucas graduated in computer engineering and got a master's from PESC at UFRJ, the nearby Federal University of Rio de Janeiro. He's been at Hotel Urbano for some years now, and he's the head of their data science team. And today he'll tell us about a data-centric approach for machine learning applications development.
Okay, thank you. So, yeah, I'm Lucas. I'm working as this head of machine learning and data engineer at Herb. So we have a lot of problems over the last year, some interesting things. And I will talk about this data-centric approach for machine learning application development. So give you an overview about the problems that we face when looking data in industry and some techniques that we use and maybe some opportunities to be researched. So okay, first giving you some context about Herb. We are a tech company that works in travel. We are based here in Rio, in Barra da Tijuca. And we sell like hotels, accommodations, travel packages, activities. So it's all products that we sell. And we are trying to use technology mostly to improve every experience that we're having when traveling. So that's Herb, that's our company. We are one of the largest travel companies in Brazil and Latin America. And we have the area of data, we have the data analytical team, 25 members around. This number keep increasing over time. And we have 3 teams, data engineers, the folks that are responsible to handle the big data infrastructure. So we deal with terabytes of data every day, new data, a huge volume of data. So modeling, the databases, etc. We have the business analysts, the folks that build the KPIs, the dashboard, they generate the business insights, and of course the machine learning engineers and data science that are responsible to build that fancy models, the algorithms, the optimizations, the automations. So I put this slide here to highlight that data projects are a team project, a team sport. So you need all these 3 folks in some way to build a quality project. And maybe it will become more clear during the presentation. And here I would like to share a little bit about my vision, how I face this machine learning project at Herb and in other industries. So we start with a business problem. Someone comes to you with a problem that these people would like to solve, maybe related to churn, credit, prediction, revenue prediction, something like this. So I have data, and as it is a data project, a machine learning project, I would like to use data to solve my problem. And okay, so I have this data set. It can be a pretty huge data set on a structure, and I go to this cycle of machine learning modeling. What is machine learning modeling? A good abstraction is, okay, I start with a model, and a model is my mathematical abstraction of the world. I try to represent in some way in the computer, in the statistics, in some other place, how I think that I can model the world. And so I did my modeling, okay, I did my model, and I pick a loss function that connects my data, my patterns that I observed from the past, with my abstraction of the world, that is my model, and then I use an optimizer. So my optimizer will make this connection better. Will optimize my abstraction of the world, my model, to better fit my data, my patterns that I observed from the past, according to my loss function. And then I use my evaluation metric, precision, recall, F1, ROC, FC. We have a lot of metrics to evaluate the results. So that's the machine learning modeling cycle. I keep iterating on this, trying different solutions. And then I have the business evaluation metric. That is the metric that really matters. If you work in the industry, that's the metric that people will ask to you. They don't actually care about your precision, about your recall. They care about the metric that moves the needle. If your model is improving the customer experience, improving the way that the revenue, reducing the churn, etc. Okay, and we can get in from this. So notice here that we have the data and the machine learning modeling cycle, and the data is static. I'm not changing anything in the data, and I have this cycle that I keep iterating and try different solutions. But here I can see that maybe ML, machine learning, is the art of mining signals from data. So I'm fitting my abstraction of the words in these patterns that I observe in the data. So I'm mining signals. I'm trying to extract signals from this data. And then I have also this other fact that AI is not so smart. I don't have general AI yet. Maybe Elon Musk don't agree with me, but it just knows about how to observe patterns from the past. And use this to answer some questions. But the AI need to have good questions, good signals in your data, the data that you provide to your model, to your algorithm, to then have good answers. So I'm trying to extract these signals. So make a lot of sense, take a little bit more time to look this data set and maybe improve the quality, improve the way that this data set is building, because your signals will be much stronger and you don't need to make a lot of effort to extract information from this data set. And that's exactly the idea of the data-centric machine learning. So first I have the model-centric. That's the way that we are used to do machine learning. So I collect as much data as we can. I keep collecting data and build these massive data sets, so billions, trillions of data sets, image, text, etc. And I keep collecting. I don't really care about quality. And I start optimizing my model. So I try my linear regression, it not work. I would try another complex model, polynomial regression, it not work. I try 3 models, maybe it not work. So I go into neural networks, deep networks, and even more complex models. Or I have the data-centric. So it's a little bit different. I'm much more interested in the data. So my idea here is, OK, my model will try to extract signals from this data. So maybe a good idea is to pay attention in this data and check if the data has quality, if the data is represent my desired phenomenon, if the data have noise and the proportion of noise and signal in this data. So I will not need to dig deeper and deeper and deeper to extract signal from this data. The signal will be in the surface. So I can use much simpler models and extract information from this data. So that's the core idea. And here we have Andrew Ng. He's the professor of Stanford, founder of Coursera, one prominent researcher in the deep learning field. He's a huge advocate of data-centric AI. And to show his point, he proposed a competition. This competition is it's like a hackathon or a Kaggle competition, for those who know Kaggle, but with a key difference. You can't change anything in the model. You have a fixed model, you can just change your training data set. And the idea is how much you can improve your performance with the same model, with the same laws, with the same optimizer, just changing your training data set. And it starts to sound very reasonable. If you look the data set, it's an image data set. Sometimes you have a lot of noise in the background. Sometimes I have labels that I actually don't know what means. So this third label, if I put it in my data set, my model will try to fit it in some way, will start to hurt my performance into the good data. So it's a good idea to improve the quality of this data set. And that was the result. So the baseline, again, using exactly the same models with the same hyperparameters, the baseline accuracy 0.64. And the winner, 0.85. So the winner increased a lot the result, just improving the training data set, just improving the way that I'm showing patterns to this model and make it learning easier.
Sorry, may I kind of ask a question about this one? Because you showed examples like removing of noise or removing outlier, I would say.
Mm-hmm.
Then it appears a question how you remove it. Because if you do this with machine learning, this is a bit, how to say, cheating. This data-centric, because you just include one more machine learning algorithm in your pipeline, basically.
Not exactly, because like the data that we use to train this performance, you don't have access. So you maybe try, oh, I will remove every data in the trained data set that I think that's noise, that's not so good. But you remove so much data that your model will not generalize. So you have problems.
No, I understand that this is not like indeed it works,
Mm-hmm.
yes? But in that case, when you say data-centric and you want to change the data, you mean by eyes, by machine learning, by...
Okay, so good. I will talk about this in some of the next slides. But it's a great question, because that is exactly the question. How I can improve this without cheating, without just like starting changing things? And the three questions, actually three key questions here. The first one is, my data complete? So the data is covering all the use case that you have. So all the labels, all the possible cases. Your data is correct. So as we mentioned, like I have like weird labels, I have noise in my data set. How can I check this? How can I remove this? How can I change this? And does my data correctly represent the desired phenomenon? So I have this business problem that I would like to work, but my data, what's the relationship of my data with this business problem? Is the correct representation or not? So, okay.
What happens if you have something good with some size of data, and then you have suddenly access to 10 times or 1,000 times more data? How do you know that this will generalize?
Yeah, it depends of the data. You don't know, because if your data is pretty similar, maybe your model just don't generalize. You want to have, if you increase the size of your data set, you'd like that this data is heterogeneous, because it will help your model to generalize. If you keep pushing the same exact data, it will not help so much. That's the core idea. Okay? But we'll talk this when we talk about active learning. That's an interesting point. But okay, data can be incomplete in a lot of ways. The first question is, is my data complete? And data can be incomplete in a lot of different ways. We can have missing values. So missing values occur when my system fails and lost the tracking of user or tracking of information because of some reason. Or maybe you have some form in your system and user forget to fill it. And we actually have a lot of techniques to try to fill this blank here. I can use interpolation techniques. We start with simple techniques, just averaged. There's common values. And I can like increasing the complexity. I can use like KNN to have the nearest neighbors and use the most common value in the top 5 nearest neighbors to fill this blank. And I can even use much more complex techniques. I can use the generative adversarial networks to fill this blank and interpolate. So a lot of techniques to fill this missing value, but carefully, because I don't like to insert like a lot of signals here, because maybe I'm overfitting, maybe I'm cheating, but there is a lot of techniques. I have missing use cases. That's where, for example, I'd like to build a model to classify a species of a dog, but I don't have any example in my data set of bulldogs. So my system will not work with bulldogs because I don't have this use case. I don't have this label. So it will just not work. And so we have some proposals to work on this. We have few shot learnings, 0 shot learnings, but the truth is that we will need to go to the field and in getting more data to train this. And you have missing features. Missing features are information that you think that is important to solve your problem. So like trying to predict the growth of a country, maybe the growth of the last year, the percentage of unemployment, etc. And building these features is difficult. It's kind of an art today, so we need to do a lot of transformations. We have algorithms that try to use correlations and use the information that I already have to build these features. And it's pretty difficult, and maybe some of you ever heard that, okay, I don't need to do this feature engineer with so much effort anymore because we have deep learning models. And like deep learning models will generalize, and so just put the raw data and it will work. Yeah, maybe. But okay, let's look at this deep learning parameters, the number of parameters of deep learning for natural language. It's keep increasing in orders of magnitude. And today we have models with hundreds of billions of parameters. So it comes with a price. If you'd like to train a model that will just generalize with the raw data and it work, we don't need feature engineering, you need a huge data set in the same order of magnitude with billions, millions of parameters, of examples. And so you need labels, because maybe your missing data is your target. You don't have labels. So how you create this label is difficult in industry. For example, at Herb, to convince someone to label you a data set with few thousands of examples. It's pretty difficult to convince someone to label to you a data set with millions of examples. And of course, you can go to a crowdsourcing such as Mechanical Turk that you pay some cents for someone else to label to you. But even this can become expensive if it is billions of examples, or if you are in a field where you need skilled people with skill to label your data. For example, medical image. You need doctors labeling your image, so doctors is expensive to keep labeling this. So what can I do to solve this problem? Because I don't have the labels, so my data set's pretty small. I would like to train a supervised model. I can't go crowdsourcing because it's expensive. So yeah, we start to think about some techniques to solve this. The first one is weak supervision. We have this paper here that I put in the bottom that was proposed by some folks at Stanford. And the idea here is, okay, I have a small amount of labeled data, but a large amount of unlabeled data. I would like to label as much data as I can in some way that will help me to train supervised models in the future. And instead of asking people to label one by one examples, I will ask them to create what we call learning functions. Learning functions are heuristics, like, okay, if this transaction has this amount and was in this country, and the original country of the user is this other country, so it's a fraud. A lot of ifs, or a lot of algorithms. Oh, if in this point of the image I have some blank, it's a cancer. So a lot of heuristics. And the idea is try to combine, try to aggregate hundreds of these learning functions in a single discriminator that will provide me probabilistic labels. And so I will use, like, for example, for the same example in my data set, I can have 3 or 4 different results according to my learning functions. And I would like to get a probability of the true label from this, and then use these probabilities to train another model. To train, for example, logistic regression, neural network, or any other model. And the idea is, if I use these probabilistic labels together with my golden labels, the labels that I initially have, I will have better results with my data set, because I will increase a lot my data set, and then my second model will generalize in some errors from my heuristics. And the paper shows some results that will increase even 10% in accuracy in a lot of cases with military and US and in other companies. And we also have active learning. That's another technique to help us to create data sets where we don't have information about the target. The idea here is pretty simple. We have a lot of techniques to implement this, but I will show you the general idea. General idea is you have a small set of labeled data set and a large amount of unlabeled data. And what you do is you have people to label data for you, but not so much, just some thousands of data points. So what you do is you train a model, and then you find your decision boundary. And you keep, you pick the points just in the frontier of this decision boundary. These points are probably the points that are harder to classify, that you don't exactly know what's happening. So you put these points, and then you find similar points to these points in your unlabeled data set, or you put it together. So different implementations to do this, but that's the idea. So you pick these points that you don't have the label, but are near your frontier, and then you ask someone to label it to you. And you keep doing this. Like, you iterate on this, and the idea is that you label your data much smarter, because you will label the data that are maximizing the gain of information to your model. You're not just labeling data that's equal, that will not provide you new information. So the idea of active learning is this, and you have different techniques using sampling and other things to improve.
It might be the case that it depends on the question you ask, the problem you want to solve.
Yeah, but because to do this, we'll need a training model. You need to train the model, like your abstraction, specifically for the problem that you'd like to solve, and then we'll keep iterating. You don't use like, you can, of course, use a more general model here, but it's not recommended. Okay, that's a case that we have at Herb just to exemplify. We have, for example, data coming from the same hotel. We don't have the data from the hotel coming directly for our databases. We consume information from our partners. So the hotel go to partner 1, put some information, go to partner 2, put the other information, and we consume information from these partners. But the problem is that the hotel owners are not so consistent. They type the address different, they type the name different depending on the partner. The information is deprecated, so partner 1, the hotel has 10 rooms, partner 2, 11 rooms. So I would like to do entity matching and discover that it's the same hotel. But we don't have labeled data set. We have just a small set of labeled data set, and we try to convince someone in the company to label more data, but we have millions of hotels, so it's pretty difficult to convince my commercial team to do this. And we use these techniques. So I put just one feature here just to exemplify, but we have a lot of features doing this. So I create a data set with like hotels with easy examples that I know that are not the same. I like just some combinations. So Business Beach, Hotel Nacional, pretty different names. And I know that the label is false here. They're not the same. And then I create some other examples like Business Beach and Atlântico Búzios. I pick like data hotels that are similar, that I use the lat long to pick similar hotels that mostly have similar names. And I create hard negatives, hard examples that I know they're not the same. So I combine this with my label data set and then use active learning and keep iterating. And we end with a data set of 1.2 million examples in the end and 99% of accuracy. It's a pretty huge, pretty difficult problem to solve because the way that people put this information is completely not consistent. And the second question that we talk about is my data correct? So, okay, I have a large data set. I have a lot of data, okay.
When you talk about the deduplication case, how do you measure your accuracy here? Do you have
So, okay, I use my golden labels, like my data set that I know the results. I pick some part of this data set and I keep hide from using the testing. And then we deploy the model and start to see the results because that was the only way. And just like we have some type that is the gray zone that we define. That is the predictions that we did with some confidence or around some confidence level. We sample some of these predictions and send to be analyzed for some folks in the company. And they say, okay, from this sample of 100 examples, half are right, 9% are right. And I use this subsample to analyze my results. So the second question here is my data correct? So I have a large data set. Is data correct? How is the proportion of noise and signal here? How it works? And the first thing is detect if system and data collection are properly working. So I'm collecting the right data. I'm collecting data that's not just noise, because I'd like to stop it and collect the good data. And some real cases that happens at industry, that happens at Herb, is system fail or intermittency. So I put a new deploy, and this new deploy just have some kind of fail, so I stopped tracking some information. I lost some information for someone. Broken contract, so I used to use the metrical system, and I changed to the imperial system. That really happens in a lot of cases. Like, people just change the way that are measuring something, and this metrical and imperial system is a good case because it was a special problem in the past. I don't remember, some special ship exploded in the past because of this. And we have outlier events that we have outlier event that I know, such as Black Friday. So I know that Black Friday will be an outlier, but I don't know how much. I don't know which kind of outlier. So how big will be? I don't know. And outliers that I don't know. For some cases, Neymar tweets about some destination and people start searching about this destination. I don't know why, and then I discover. And we use some models to detect anomalies. In industry, some things that's pretty important to detect anomaly. Again, I'm detecting this anomaly to decide if I will remove or keep this data.
Yeah, the anomalies might be what is most important, because if you can predict something like Black Friday, you are very happy.
If I can predict Black Friday, yeah, but I would like to predict how good it will be Black Friday. I mean, I know that I will increase my sales at least 100%, but I know if it will be 100 or 200% an increase. And I would like to understand what happens, just to say, okay, in Black Friday, let's say my systems stop working if I have a high volume of users. So I can have the anomaly of Black Friday, but I can sum it with some bug. I would like to distinguish between these two things, like anomalies that I know and bugs that can sum up with this. And yeah, okay. And here, the anomaly detection is to decide if I will keep this data in my data set, which in some cases is important, or if I remove. It was an anomaly, it's just noise. And explainability is pretty important here. So we use mostly at Herb isolation forest. So 3 models are good because I can just the way that isolation forest works is you split your data, you try to classify your data in some class. And if it's possible to separate the data in the first splits, and the branch is pretty short and have few examples, probably this is an anomaly. And it's pretty good because it's explainable. So it's easy to check with some other folks in the company, so we use it a lot. And also clustering. So I cluster the data and I see and I check if the cluster is pretty separate from the others. So I manually check the cluster and say, okay, that's anomaly, that's not anomaly. I would like to consider this in my data set or not. So we use these techniques a lot. And we also have systems to monitor the data quality of our data set. This is a general dashboard. We look like missing data, data freshness, data volume, table anomalies. And for example, in the time series anomaly, I would like to decompose this in the trend, in the seasonality, and understand day of week, day of month, etc. Because maybe if I can be naive and add just a threshold. Oh, if it passes this value, it's an anomaly. But maybe my sales is consistently huge in Friday, for example. I have more sales in Friday, so I'd like to decompose and not just put a threshold. And the one interesting thing here that we are trying to solve, that we're not solved yet, is how to add assumptions in this anomaly detection. Because we can use Bayesian models, we can use sample strategies, but I think that's a good opportunity for research, because how can we add assumptions? Because I'm increasing 100% my my investment in marketing to Black Friday. So I would like to consider it when predicting, when detecting if it is this point at Black Friday is an anomaly or not, or days around Black Friday. Of course, we can do the way that we do this today. We train a different model to predict this point and consider this marketing investment, for example, as a feature. But probably we can use better ways to solve this problem, but that's the way that we do. And we also have this that is pretty interesting. That's the automatic root cause analysis. Instead of just pointing, okay, I have an anomaly, I'd like to understand this anomaly. So where this anomaly is happening and why this anomaly is happening. So I pick an anomaly and I find a subset of data where this anomaly is happening more. So it's not the image, but we have a good use case that's good to explain that. I have these anomalies happening just in 1% of the data, but in 50% of the data that's coming from iOS. And in 99% of the data that's coming from iOS version 2.0. If I can detect it automatically, it's much better to me because otherwise, if I train my model will keep the performance, but the performance for this specifically subset of iOS version 2.0, for example, will be very bad because my data is not working. So this is also a good opportunity to improve that we are trying to improve at Herb and maybe in research is not just detect anomalies, but embed the explainability of this anomaly in the technique. Here we just analyze subsets of the data and try to find the reason of the anomalies using slices. And we also have human error and lack of label consistency. So yeah, muffin or dog. So if you look at this, I have muffin, I have dogs, which is a muffin, it's a dog, what is that? What's the first figure, is a muffin, a dog? So maybe in some cases it can be confused. People can be sleepy, so it's a muffin or a dog. And it happens in real cases, not with muffin and dogs, but at Herbie we have, for example, a system where people come to us asking for customer support, and in chat, they use text, and someone provide the support, and after providing the support, these folks will label the data, provide, the ticket motivation, the cancellation, if it is a cancellation, customer sentiment, type of questions about the product. So we have some classes, and they will put these classes in the text. And it can be very large conversations, maybe conversations of 1 hour in the chat. But the problem is that labels are not consistent because we are dealing with humans and dealing with very large chats sometimes. So people, what was the motivation? Maybe this, maybe that. It can become confused. And we have some techniques that we use to help us with this. One of these are confident learning. It's a pretty new technique, which was proposed by folks from MIT, I think 3 years ago, that in a PhD thesis. And the idea is the focus is when finding labels are wrong in your data set. So finding labels that someone label as X and a true is other value. So how can I do this? I have a small set of label data set, and I train a model. And after training this model, I will analyze the join probability between the true labels and the noisy labels, the patterns of error of these models, and start to setting some thresholds. This second matrix here, they use some thresholds according to the flip probability that they call. Flip probability it's not exactly a probability, but what is the chance of classifying a fox as a dog, a fox as a call, and vice versa, or a fox as an actual fox. And I start to analyzing these join probabilities, and when predicting some example, when doing some inference, I will analyze the confidence that I have in this prediction, compare with these thresholds and then like having good candidates that maybe are not the right labels. So we're trying to do this comparison. There's a lot of, it's not so easy, this technique. It's quantum information proposals in the details, but that's the general idea. Use the joint probabilities, the flip probabilities to compare with your confidence in your prediction, and you try to find noisy labels. And here we have some results, which is important here, because let's say ImageNet. ImageNet is a data set that everyone, every researcher, every industry practitioner use to train data sets, to train models, to propose new models and evaluate benchmarks. And so we have an example here using confident learning. So in ImageNet, I have the label sunglass for the first image. And with CleanLab, we detect water bottle. So they send these two labels for Mechanical Turk, which is a crowdsourcing labeling system. And Mechanical Turk say, OK, it's above. Mechanical Turk is people actually looking the data and putting labels. It's above sunglasses and water bottle. So if you are a researcher and you are proposing a new model, and your model predicts here water bottle, your model are not wrong. But if you train this in the ImageNet, it will be considered an error. Also, in the other image, we have bra, same in ImageNet. But the actual label is bikini. So again, if you're proposing a new model, and your model say, OK, we have a bikini in this photo, it will be considered an error. So if you are benchmarking with other researchers, maybe the other researcher will have advantage over you because they are doing errors. So it's pretty important to understand the truth in this data set. And the final question is, does my data correctly represent the desired phenomenon? So what's the relationship between my data and the problem that I'm trying to solve? It depends a lot of the context. So let's do a quick exercise. Okay? Let's build a cat classification system. So first, is a cat or not? It's a cat, probably. It's a cat, of course. Is a cat or not? Yeah, it's a cat again. Is a cat or not? Your label? Yeah, maybe it is, maybe not. Is a cat or not a cat? Depends. So it depends a lot of your context. Because, OK, lack of context. If you're doing a pet shop, of course, the two last ones are not cats. But let's say you are doing biological research and considering family of species in some ways, and ancestrality, I don't know. Maybe it is. So the context of your labels, understand from where your labels come, what was the instructions that people give to your labelers is pretty important. Because otherwise, your system will keep doing errors, but are not truly error. Or you train a model, OK, it's all cats. But OK, now let me transfer learning to a pet shop system. Oh, it will be a problem. So you have gender bias in your data set. We have human resources system that's true. It was, I think, 2 or 3 years ago that just reject any women applying to some positions. Because people don't pay attention in the training data set. In the past, don't have any women in some positions, in some job position. And they train the model, and the model has a lot of bias and just keeping these kind of errors. The same thing for face identification for suspect. They are trying to implement this in England, United Kingdom, and they stopped using this because the data set has a lot of bias, and they are doing a lot of more errors with black people. So they're having a lot of trouble to implement this, and it's a kind of barrier to implement AI in the actual world, in the real world. So it's a problem and understand what bias is in your data. So lack of domain knowledge. If you are creating a data set for medical image, for example, depending of your labels, the specialization of your labels, specialization of your doctors, it will vary a lot the type of labels that you have. So it's like cancer or not cancer can become a cat or not a cat, depending of the context of your doctor. And the last thing I'd like to show you is concept drift. So OK, we understand that the context of the label depends on the context, but the context can change over time. Okay, so here we have our training data set. We train a model when we achieve this first result. A decision boundary in the original data, my model divides the green dots and the blue dots. Pretty impressive. It's like 100% of results. So let's look the image on the right. So I have a drift. Like, let's simplify here and say that every example, I'm predicting the probability of epsilon given x. So if probability of x change, so my data distribution change, it may become a problem because I can have data that I never seen before. My data distributions can, like, bias can happen here, but maybe not so bad problem because my decision boundary is still the same. So my system will keep working. But if the conditional probability changes over time, and it will change, you have a problem. Your model just stopped working. The model that works in the past with patterns from the past, the patterns do not happen anymore. The fundamental concept of these patterns just change, and your decision boundary stop working. Some real cases of when it's happening with us, with HERB, airline ticket prices. If we have models to predict the price of an air flight, so it just stopped working. Just stopped, because after COVID and during COVID, the nature of this phenomenon completely changed. So the model not work anymore. If I would like to use past data to train my model, I start using a lot of sampling techniques, weighted sample according to time. So a lot of fancy techniques to solve this problem, and maybe it's not solvable in some cases because I just need wait for more data in the new nature of the phenomenon. Accommodation search behavior. So we noticed this, Airbnb noticed this, Booking noticed this, every company in travel noticed this. After COVID and during COVID, people start searching for long accommodations and accommodation near the original place. So it's a pattern that just not exist previously. No, exists, but much smaller. So the way that people search change. And with this, we need to consider all the past data that we have and build a new recommendation system, a new search system, because the interest of people just change. Our flight acceptance pattern. So at HERB, we try to understand the type of flights, the hour, the day of week that people would like to travel. And after like home office, working from home, this changed a lot because now I can like travel in the middle of the week. And in the past, it was not possible. So it's not working anymore. I need to reevaluate my patterns from the past and like build new abstractions of the world. So my concept drift. And the important thing here is to detect when it's happening, when the conditional probability is happening. And this is pretty difficult in some cases because you have cases where you have feedback. So you are putting some label and someone then are giving you the real label. And you have cases when you just don't have feedback. You just put a label and believe that's right. So the way that we deal with this is we have some tricks to do this because, for example, if I don't have access to feedback, I can just evaluate the probability of X, the distribution. I can use, for example, slices in the time windows and compare and use metrics such as Kublai-Leibniz to combine these two distributions and see if something is changing. And if I have feedback, I can use an adaptation of this method. For example, getting my model, use the residual of the warehouse, and then comparing the residuals distribution using the Kublai-Leibniz or other metric. But it depends a lot if I have feedback or if I don't have. And key takeaways, iterating data many times is more effective than iterating the model. So we look a lot of use cases when data is not right, when labels in your training data set is not right, when you can increase your amount of training data. So a lot of times it's better to look to these points, anomalies, quality, noisy label, etc., than keep iterating in model, because like you start reading paper and more complex models, but maybe a simple solution will solve your problem if you have good data. If you use models that may need label data, be prepared to perform imputation techniques, so interpolation techniques, techniques to generate target, because it's difficult to have a large amount of labeled data set. If you're dealing with open fields such as a general image classifier, a general test generation, it's okay. But when you face industry problems, real problems, you don't have this data set. No one ever labeled this. So you need to be creative and use these techniques to generate data. And you need some principles to generate this data, because otherwise we will insert noise in your training data set. And the third one is context. Context is essential when building ML models. We saw the cat, or not the cat example. Or if you're training a model and you don't know how it was labeled, your model will predict right the wrong thing. So you don't want this. It will change, and you can change over time, as you mentioned in COVID. So these are my key takeaways, and thank you for your time.
So thank you very much, Lucas. Do we have questions? Yeah.
I think I can.
Okay. So thank you very much. Actually, that's I have several counterparts with my previous experience. Yes, but question would be, what are the main challenges and what are mathematical tools which helps you to solve those challenges? Yes.
Yeah, the main challenges, I think, are the lack of fundamental research in this field, because we have that's most engineering techniques. People start proposing heuristic, proposing techniques to solve this problem, creating libraries, but we don't actually have much papers about this. So we have papers, so as I mentioned, from Stanford, from MIT, from good institutions, but it's 1, 2, 3, 10 PhD students. It's not a field that academia is really working and developing a lot of things. So the main challenges here is to find techniques that you can really trust and be confident that will not change over time and implement in some different way, and you can understand what's happening. And about the tools, that's maybe other challenge, because people that are starting to create these tools, they are creating enterprise tools. For example, the paper that I show you for weak supervision for Stanford PhD students, it was 3 years ago, I think 4 years ago, that proposed the first paper. It's now worth $1 billion company, that's Snorkel.ai. So it's pretty expensive to use these tools. So we lack open source tools, like tools that I can just install and perform this in my computer. Active learning is the same. I have a lot of papers about active learning, but if you want to really do active learning at scale, it's difficult to do in your computer. You need to go and use some of these enterprise tools, because the paper have some details, but you start facing some barriers, some things not working the way that they describe, but these same things work in the enterprise solution. So we start questioning what happened here. So I think that, yeah, maybe that's the main difficulty. Most of these points here are engineering and not solid research, and the tools are all enterprise.
So I just was encountering this, what you call might be active learning, yes? So when you ask which points should be labeled, yes? But okay, I encountered this with low dimensional data, yes? Not like 20, not like an image, which is, I don't know.
But you can use it with image if we ask.
No, my technique is is not allowed for
okay.
multidimensional, because it would take infinite time. Yes.
Okay.
But then you tell that there is no mathematical models to try to answer your question, basically.
To try.
To try to answer to this data quality, data-centric, data labeling, data
Yeah.
everything. No mathematically posed question. Yes.
Yeah, there is mathematical equation and mathematical papers, but my point is there is few mathematical equation and mathematical papers. So I need to trust a lot in these researchers, and I need to reading a lot of papers to try to understand this specific way of thinking about these researchers. So if I have more papers and more information, it will be more like peer reviews, more like questions around these techniques. Because some ways it's difficult to question something that has a level of complexity and an increasing level of complexity. So yeah, my point is we have mathematical equations here, but it's not so much. We have few. That's one challenge.
Can you send the references that you have?
Of course. Yeah, of course.
So, okay, Lucas, thank you. Not sure if this is on. So thank you so much for the talk. A lot of the issues you've raised strike close to our heart. So we've been working with recommendation systems. We have some people working with change point detection. And interestingly, we were working with credit prediction during COVID. So this is probably one of the best sort of call to arms for this idea of data-centric AI, because of course can't even think about retraining models going through a pandemic. So using that as a specific concrete example, how did you guys, so we in academia have of course, the luxury of, just saying like, okay, this problem is just too hard right now. We're going to wait 2 years. We'll have, pandemic data we can train then. But you guys don't. So when COVID happened, how did you guys first react in terms of all your systems? And then now, sort of 2 years later, looking back, what do you think would have been the right approaches in terms of modifying your data for the pandemic?
Yeah, the approach that we did was mostly getting assumptions from people that understand about the business. So, this last month will be more representative than the last year or this other year. We're collecting these assumptions. And we use these assumptions to sampling data and build a new data set. So I start modifying my data set so in a way that the weight of the last months are much more than the other months, or maybe the last month and I just ignore the last month because it was something happened in the last month. So we did a lot of sampling stuff, combining assumptions. That was one of the points that I mentioned previously in the presentations. I'd like to have, maybe it exists, but I don't know, some way to input this information in the model easier than just sampling in different ways. Of course, we have Bayesian models, but I can just change my model completely to a Bayesian model. So I think maybe looking from the past, maybe trying to develop this kind of model if not exist, or research a little bit more about how to insert business assumptions, business prior probabilities in my data to change the model behavior automatically. But the way that we solved this was sampling and trying to figure out what's happening. We also changed the way that we see some problems. We stopped looking for the prediction and we start looking for the intervals. So I'm not interested anymore in the prediction if 1, 2, 3, but if it is varying, okay, I have 99% of confidence that my interval will be between 1.5 and 2.3. So that's one of the things that we do. And we start looking, we also start using quantile loss, for example, to be more conservative, to be more aggressive. So but some of the models just stop working. We can do nothing about this.
What are exactly the things that you are trying to predict in this kind of concrete example? For instance, when you predict the price of an air ticket, how does it help you to?
Okay, yeah, the Herb model is the core of the Herb model. For example, how Herb works. Yeah. Okay, you buy a destination. You don't buy a hotel or a flight ticket. For example, you go to our website and you buy, oh, I'm going to Miami next year for 2,000 reais. Just it. You don't pick the hotel. You don't pick the air flight. You don't pick nothing. You just suggest 3 dates. And what we do, we'd like to predict the price of these flights in the future to create the present price that will sell you. So if I'm predicting it wrong, it can be a huge problem in the future. So yeah, so in this middle time, this year between you buy first and like you actually travel, we do a lot of things. First, we try to find the minimum point, the best point to actually buy your flight and to actually buy your hotel. That's one of the points. The second one is to identify places where the price is just increasing, and I will not find this price in the market anymore. So like creating like an alert and say to my commercial team, oh, go to this place, because if you don't negotiate a price here, we'll have a problem here. So it happened, for example, in the beginning of this year, I think, with Maragogi or someplace in the northwest region, and we just use all accommodations that we have in the city. So we don't have rooms anymore to put places in the city. So we need to start negotiating with hotels to having more rooms, because otherwise we'll need to buy any room available, and the pricing model of hotels and air companies, they have also an optimization function that increase the pricing according to the demand. So I need to detect this earlier in the way that I buy these tickets before they notice that I would like to buy this much of tickets.
There are similar problems when in the stock market, and there are a lot of studies for that, so you can go from one field to another.
Yeah. In stock market, that's a similar problem is when you look dark pools in stock market. What we have at Herb is actually, in stock market we have dark pools that is, I send a lot of orders to somewhere, so I have a pool of orders that no one have access, and then I can execute these orders. But if people have access to this amount of order, for example, a large order to sell something, they can just sell small amounts before I sell the thing that I'm interested. So it's the same in our case. I have a dark pool of, for example, this year, I can say this now, but this year we'll put almost 1 million of Brazilians in Orlando, in just Orlando. So I have a dark pool of 1 million Brazilians that I would like to put in just one place. So no one know about this. If the places of Orlando know this before, they'll just increase the price, because I need to put these people there. Because if otherwise the people will put, like, you start to go into Procon or someone else. So I need to put whenever the price is. If it takes me the double of the price that I sell to these people to put these people in the place, I will need to do this. And the hotels know about this, and the airline companies know about this. So it's a dark pool. Like I need this upfront advantage to buy the assets in the market. And yeah, it's a good parallel. We use a lot these similarities. But it's a difficult problem.
There are lots of papers already.
Yeah. It's a pretty difficult problem, especially because of airline companies. Like, airline companies invest a lot in revenue models. So everything that we do, they adapt. So it's like a game.
I want additionally to make a comment. Actually, what you are explaining is more like a game theory rather than machine learning.
Yeah.
You can use machine learning in scientific theory, yes.
Yeah, that's something that we are trying to figure out how to, like, we are keep improving our models, but this is the core of Herb. So that's the problem that we're trying to improve, because it happens. Sometimes we just are wrong about the prices, and we pay a lot for this. Because if I predict 1 year, oh, it will be $100, and it's $200, I lost $100 per sale, and it happens sometimes. So it's pretty difficult.
It was hard time when the
Yeah.
pandemic started.
But no, in the pandemic, actually, it was good for us. It was good because what happened is that people are not allowed to work. So their money keep with us with much more time, and we have time to do negotiations with hotels. We have a lot of money from people that already buy, and we know that we, in some point of time, will need to put these people in this place. And the hotels and the airline companies have no money in the pandemic. So we start buying all the inventory in the pandemic, and we are using it today. So it was good for us, actually.
Well, maybe have time for one quick question, if anybody has one. Well, if not, let's thank our speaker again.
Thank you.